everyone, welcome back to our channel Two Data Detectives. Last week, we briefly discussed the idea behind MemGPT. This week, let's look at how MemGPT gets its ability to mimic infinite memory using virtual context management. Let's have a look at the architecture.
You can see that in the architecture diagram they have provided in the paper. So if you look at the architecture, what they have done is in their virtual content management, they have two main components. One is called the main context. That's strictly limited to the max token limit of the LLM that they're using. In addition to the main context, they have an external context. How they draw parallels of these two components with operating systems is the main context is similar to the RAM that we have in the computer, and the external context is similar to the
hard disk.
Disk memory. Yes, correct. That's the hard disk. So inside the main context, they have three components they're talking about. The first one is system instructions, very similar to the system prompt that we have, which we're sending to any LLM. Next concept is the conversational context, which is an interesting one. So you know how in RAG we have a system prompt and then we get snippets of documents, and that's where the context of the conversation is captured. So they have a similar concept, but this is kept in a queue, and that queue has a limit. But it has the recent history, right? So the idea is if you're about to run out of your token limits, then this queue gets iteratively summarized, which is pretty cool. And so this way, if you want to keep the context of a long conversation, you're still able to do it by summarizing the recent history and by maintaining it within the main context.
So it works exactly like a computer.
Exactly. And they also have what they call a working context, which has the ability to move in and out more information into the conversation and can change a lot over the life of the conversation. And in the external context, they have two concepts. One is called the recall storage. This is basically if you have a long conversation, you store all the historical events of the LLM in there. It's an uncompressed queue. It's like your active memory. And then you have the archival storage in your external context, which stores your external documents like your data files, PDFs, from which you get the relevant context for a user query. And the most important part, I think, in this paper is that they have created these pre-prompts in MemGPT so that it has the ability to do self-directed editing and retrieval. What that means is that in the prompt, they give detailed descriptions of the LLM's memory hierarchy and their respective utility. And they also define function schemas, which they complete using natural language descriptions. So that's very clear. Let me show you an example. So here the MemGPT says, "Hello Chad, it's a pleasure to finally have a conversation with you. I know you're interested in these things. Why?" And then it says, "Okay, I'm Samantha and this is why I like these things." And then suddenly MemGPT says, "Oh, it's generating a system message saying you're running out of context memory and the history needs to be trimmed, and make sure you have saved your history." So as a part of it, it's able to figure out that you're running out of memory. And in your working context of this conversation so far, you're not going to lose it. You're going to save that memory. And as a result, you're not losing anything in your conversation. So this sort of chaining happens with different events, and these events can be user messages, system messages, user interactions, and timed events that are running on a regular schedule. So when I read this paper, I felt like, oh wow, that's a cool idea. It's very similar to how an operating system would work. And I feel like it has some similarities for React as well. If you recall, to solve a problem for a client, we used React, right? And in that problem, it was solving a mathematical question, and we had to call different mathematical functions to solve the problem, and we used React to figure out what was the next function to call. And I feel like it's a very similar concept that's happening here with MemGPT, but that action space seems to be the typical function methods we see in operating systems like caching, paging, page replacement, caching strategies. So the action space seems to be simulating something that's happening naturally in operating systems, and I feel like it's a very interesting concept to try out in LLMs. It's like LLMs having their own brain and being independent of the context with and having the ability to run on its own.
Yeah, exactly. I guess it's a whole different way of interacting and responding to the environment, generating new actions. It's the computer's way to generate new actions. But if the large language model in MemGPT generates wrong messages, would it just crash the operating system?
Yeah, that's an interesting question. Yeah, I think at the end of the day, MemGPT, what it's doing is it's just generating text. So if it generates and then calling a function based on that text. So if it's generate the wrong text, I don't think it'll crash per se, but it'll probably start generating irrelevant answers, and that's where you'll have to have a fallback plan and intervene and take corrective actions.
So it's exactly like making a mistake in a conversation instead of making a mistake in a computer.
Exactly, right? That's how it is in any conversation. All right, so that's all we wanted to share with you today. We have discussed the MemGPT paper and the architecture today. In our next session, we'll have a look at the MemGPT code and play with it. Thank you very much.